Most of today's cutting-edge science is so specialized that it is beyond amateurs to make any significant contributions. Not so in astronomy. Some astronomy projects rely on state-of-the-art electronics and big-budget space technology. Yet many important discoveries are still made by enthusiasts with nothing more than an off-the-shelf backyard telescope. This documentary is about the Citizen Sky project. The goal of this project is to discover the secrets of a star called Epsilon Aurigae by enlisting the help of thousands of amateur astronomers worldwide. One of those amateurs is Alice Few, an IT professional from Washington State. Alice loves the night sky and often makes her way to Mount Rainier to look at the stars. It is a hot day in Chicago. 27 years have passed. While the people on the surface content with the heat, a select group of individuals gather at the Adler Planetarium. They focus on one thing only: a star system more than 2,000 light years from Earth, called Epsilon Aurigae. The eclipse is about to happen, and all are intent to this time pierce the veil of mystery that has shrouded this star for so long. What is unusual about this meeting is that most in attendance are not professional astronomers. In a unique approach to bring in fresh ideas and increase data gathering potential, business people, teachers, and others from outside the scientific establishment have been invited here from all over the United States. They are the citizen scientists. They have come to unravel an enigma.
Epsilon Aurigae is a very large star, much larger than our own sun. It's very far away, we can see it, but it's not by itself. It doesn't sit by itself in the sky. There is some other object that orbits around it, and it takes 27 years for that other object to orbit around it. And for a 2-year period, in that time, the object is between you and the star. And the interesting bit is we don't know what the secondary object is.
Chris Stefan is a science teacher in Florida. He is a long-time variable star observer and has made over 35,000 observations.
Epsilon Aurigae is an eclipsing binary star, which means if you think of an eclipse means for one body to block out the light of another. Just like a lunar eclipse, an eclipse of the moon, where you have one object blocking out the light. In this case, it would be the Earth blocking out the sunlight onto the moon. We have, in actuality, a multiple star, and that's part of the...
Steve Howe works at the National Optical Astronomy Observatory and is a member of the Kepler mission science team.
So every 27 years, you would see this repetitive time when the light from the star dims by about a factor of 2. And that dimming is caused by some object, which astronomers don't yet know what that is, passing in front of a very large supergiant star. And by studying it at each eclipse, astronomers believe they learn more and more each time. However, it's been studied in fair detail now for about 3 eclipses, and we've been confused each time.
Robert Stansel is the lead scientist on the Citizen Sky project and teaches astronomy at the University of Denver.
Pursuing some myself, but also have the privilege of operating some very interesting, unique observatories. Not the biggest in the world, but one is the highest in North America, and the other is a classic 1890s huge refractor known as Chamberlain Observatory in that latter case. A lot of people can appreciate, understand a binary star because it's a relationship between 2 astrophysical objects, or 2 human beings in a way, and normally both members are pretty visible and obvious and so on, and throughout the universe we see that case over and over and over. The problem with Epsilon Aurigae is the companion is hiding. We know it's there, gravitational effects, some eclipse effects, but it doesn't fit our usual expectations of what a companion star ought to look like, and therein lies the game, the mystery of Epsilon Aurigae.
Imagine going 1,000 miles an hour for 24 hours straight. That is what it takes to go around the Earth once. Light travels so fast, it can go around the Earth 7 times in 1 second. Yet it takes light 2,000 years to make its way from Epsilon Aurigae to Earth. At this enormous distance, all we see of the star is a single point of light, even with our strongest telescopes. This point of light varies in brightness and color over time, and that is all we have to go on. In order to learn more about this star system, we track its brightness and color. When the light dims, we know that an eclipse is going on. We draw our measurements on a graph during the eclipse to get a so-called light curve. This light curve is what astronomers use to come up with theories about Epsilon Aurigae. Citizen science projects involve amateurs to gather research data. This allows scientists to accomplish research that otherwise would not be possible. These projects also offer a unique opportunity for interested individuals to enrich their lives by participating in hands-on science.
And there's a whole citizen scientist movement in several areas. I know for a fact that Audubon and Cornell University in their ornithology, which is bird studies, they're using a lot of citizen scientists for studying birds.
If we look at the large societies of amateur astronomers here, the AAVSO as an example, that there's a lot of people in that society that have been in there for years that aren't astronomers at all. And I think the grand tradition, as you mentioned, of people who weren't essentially professional astronomers, but did so much of the founding work, not only in amateur astronomy, but in astronomy itself, has been a real, you say, a foundation for those people to carry on that work, and it's been a tradition.
Galaxy Zoo comes to mind, Citizen Sky. These are current online activities. You don't have to go to a meeting necessarily, but you can, through blogs and forums and wikis and probably chat rooms, get involved without too much trouble. And in our case, the beauty of Epsilon Aurigae is even from the worst light polluted area, you can still see the star.
It was a tradition, for example, in the early 1900s for wealthy people to go to places for the summer that were out by the oceans in the northeastern US. And they did that not because they were going to go out and do astronomy, but to be cooler and get away from the cities. But while they were out there, they noticed the skies, and they didn't see those from the cities. And many of them turned to building small observatories or funding small observatories or making measurements. And so once again, it was this kind of fascination thing that led to people kind of becoming amateurs because they were fascinated by it.
So this is going to be an up and future thing, and hopefully it's a way to get people of all ages back into science, just being interested in nature, not even a particular type. You know, it doesn't have to be just astronomy. It could be somebody studying, you know, plants or whatever. And I think this is going to be a very, very popular movement.
It's very hard, I think, to be an amateur physicist and get anywhere, or an amateur chemist and get anywhere. But amateur astronomers not only can do it, they have places and meetings like this and professionals who appreciate their work and actually use it.
For example, an amateur in Australia finding this scar on Jupiter that was an asteroid, some large object hitting that planet. It was all eyes to eyepiece. It was, you know, a volunteer, a citizen scientist, an amateur astronomer out there doing what he loved, looking at the planets.
The American Association of Variable Star Observers promotes public involvement in astronomy. It has accumulated a database with 17 million observations submitted by participants from around the world. This is an important resource for professional astronomers. The Citizen Sky project that was initiated by the AAVSO provides everyone with an opportunity to participate in real scientific research. The project's goal is to understand a star that has been a mystery to scientists for many years. Rebecca Turner is the Citizen Sky project manager.
Expose people to as much as you can, and they'll absorb as much of it as they are able. And why not err on the side of trying to make people more knowledgeable? If they're not able to pick it up, that's all right. But give them more knowledge than they could possibly absorb, and then they'll absorb the maximum amount of it that they're capable of doing. The mystery of Epsilon Aurigae is one that professional astronomers, I don't think, can answer on their own. I think that they really need the help of citizen astronomers because the object is very bright, which makes it difficult to look at through very sensitive equipment, which is what most professional astronomers have access to. And for this one particular project, it's looking at a particular star, Epsilon Aurigae, in the constellation Auriga. And this star's got a little bit of a mystery, and we need as many eyes watching this star as possible. And it's a naked eye star. It's something that you can just walk outside and see from your front porch. And by looking at it and making an estimate of how bright it is and reporting that estimate, scientists will be able to take all of that information from volunteers and citizens and actually figure out what's causing it to change in its brightness, what the mystery object is that is eclipsing that particular star.
There's going to be a lot of professional astronomers that are going to be contacting AVSO and saying, okay, what's the star doing right now? We want this data, whether it be the visual, and there's some people going to be doing photoelectric, CCD studies. They're going to want all of that, and then they're going to line it up with whether they're using the Hubble Space Telescope to observe it, or an ultraviolet satellite, or an X-ray telescope, or whatever, and they can get, what they're doing basically is getting observation from all the parts of the spectrum, and then they can put all that together and learn more about the star.
Everyone in this room probably has
Doug Welsh is professor at the Department of Physics and Astronomy at McMaster University in Ontario. He is a regular contributor to the Slacker Astronomy podcast.
That is one of the valuable aspects of this particular project, is people can connect with the observations themselves. They can get a feel for the uncertainties themselves. No set of observations is brilliantly clean, and astronomy has its share of observational issues. They can be part of the analysis. They can see what other people are bringing in terms of other wavelengths, some of these properties of the distribution of colors, the spectra. They can get a grasp for what these things can tell them. And with science, one of the critical pieces is what it can't tell you.
Look deep into nature, and then you will understand everything better. Albert Einstein.
In the time of Copernicus, all astronomers were amateurs. Back then, people believed the sun moved around the Earth. Copernicus demonstrated that instead it was the Earth that orbits the sun.
Early astronomers were all different things. They were musicians, they were priests. I think one that really appeals to me has to be Caroline Herschel. She was the sister of William Herschel, famous astronomer. But she went with him to Bath to keep his house and ended up keeping the observatory. She was an astronomer in her own right.
So amateurs, they contribute in many ways, and history of science, not just astronomy, is full of examples of people who were studying things because they found them interesting and turned up some fascinating discoveries, like Schwab and the sunspot cycle, for example. Schwab was a Swiss chemist or pharmacist, basically, and over the course of time began to keep records with a simple telescope projection, the image of the sun, and over the course of a decade or two noticed the waxing and waning of sunspot numbers on the sun, and reported this to the scientific community, and it's now known as the solar cycle. Quite a discovery. Another good example, a fellow named Wilson graduated with a meteorology degree from London. His first assignment was to sit on an island in the north of Scotland and count clouds, basically. And so for his excitement and spare time, he began to experiment with some kitchen items to make clouds and see how they work. And in the process, he discovered a phenomenon we call cosmic rays. Set up his cloud chamber, and these little streaks came through the cloud. He presented this at a meeting back in London in the early 20th century, and everyone was fascinated and puzzled. And within a matter of years, Einstein and his collaborators were explaining the nuclear theory of matter, which cosmic rays are a portion of. Copernicus helped us move from one paradigm, the Earth-centered universe, to the current paradigm, which is the sun-centered solar system, as part of a large galaxy in the midst of a vast universe. And similarly, we have ideas about binary stars like Epsilon Aurigae, but we're probably missing some key ingredient that will help us understand a lot more things in the process.
Before the telescope was even invented, Copernicus realized that the sun is at the center of our solar system. Today, with the help of the Hubble Space Telescope, we can see distant suns coming into existence. Stars form inside enormous clouds of gas and dust. This is a process that takes hundreds of thousands of years. Astronomer Matthew Bates of Exeter University created a computer model that simulates star formation. We can now see in 1 minute what happens over 250,000 years. The simulation begins with a spherical cloud of gas and dust, measuring 2.6 light years across. The cloud exists in a delicate balance between pressure and gravity. Once this balance is lost, the cloud collapses into a turbulent storm of fragments. As gravity continues to gain the upper hand, each fragment continues to collapse into an ever smaller and denser cloud. Eventually, all the gas and dust of each cloud fragment collapses into one or more spheres. The extreme pressure causes very high temperatures at the center that in turn cause the emerging star to begin radiating light. This is exactly how the star of our solar system, the Sun, came into being. Our Sun is an example of a singular star. It is just as common for two or more stars to emerge together. A pair of stars together we call a binary system.
Imagination is more important than knowledge. Albert Einstein.
Nothing seems to stimulate scientists' imagination more than a puzzle they cannot solve. Indeed, the scientific method is a carefully designed system to make known the laws of nature. Yet it all begins with audacious imagination.
The scientific method, which I teach very strong to my middle schoolers in Florida, and that's where you start out with an inference, you start doing actual experimenting and testing, and you go to hypothesis stage, and then you test it more and more, and if the hypothesis continues to be supported, you can develop a theory, and if it's tested more and more and more and more, it can become a law. So this is exactly what's happening. We've got all these models of, which are hypotheses and theories of Epsilon Aurigae, and as more and more information comes in, and of course we have a lot of new technology since 27.1 years ago, that model may stay the same. It may completely have to be changed, or they might have to just tweak it a little bit to make it a lot better. So it's definitely going to be, adjusting, but that's what science is all about, isn't it?
When we look at the star, it's a bright third magnitude star in Aurigae. We can get a spectrum. The colors of that star tell us it appears to be a more or less normal F supergiant type star, very massive. Because it's in this binary, we can learn something about the companion. It appears to be comparably big and massive, but very dark. Why is it so dark?
The thing that eclipses it cannot itself just be a star. It's much larger than any known star. It has to be some sort of a large object. And you could imagine all sorts of things. The early models made it basically a large brick. We didn't really know what it was, but you could model it as a large brick, and that worked. Now, we don't think there are large bricks out in space, but the best guess for this object is a large dust cloud or dust disk that's orbiting around the F supergiant. It has to be almost as large as about a third of our solar system. So it's an enormous object that's orbiting around this supergiant. And it must be dark because we see no signature of it in visible light.
So that's why this star is so interesting. It's a supergiant, which is a relatively rare star to begin with, but it's also in a binary system, which is rarer, but it's in a binary system where there's an eclipse. So we know right away a lot more about this star than we would for an average supergiant sitting out in the middle of the Milky Way.
The prevailing idea was developed that the companion is indeed a solar system-sized dark disk, dusty material, etc., with a binary B-type star pair in its core, conveniently hidden to Earth because the disk is seen edge-on like a vast Milky Way galaxy with a central object to it.
An F supergiant is a star that started out as a very massive star, much more massive than the Sun. If we say that the Sun's mass is a unit of 1, so it has 1 times the mass of the Sun, an F supergiant was a star that probably had 20 to 30 times the mass of the Sun. It didn't last very long as a normal star because it burned its fuel at its center very rapidly. It maybe only lasted as a normal star for 100 million years, very short in an astronomical time scale. And then it became this much larger, enormous star that's on its way to its death as a supernova. So the bright star we see in Epsilon Aurigae will die as a supernova. It will do it astronomically again very shortly from now.
Yes, and that's why I'm leaving town immediately. I'm staying on the other side of Earth from this thing. It will actually do something interesting, most likely a supernova in the not too distant future. And when I say not too distant future, I'm talking hundreds of thousands of years. And that's That's the near future for astronomy. A lot of stars like the sun, they're going to be around for another 5 billion years.
A few decades ago, last eclipse, people speculated about being a black hole present because that was the new topic at the time. This time around, some have even suggested that there's some lost dark matter collection accreting this dusty material around it, and hence the low visibility of this thing despite its high mass.
I have to say that the work that has been done so far is clearly not the answer. And I think that we're finally in a state where we have all the wavelengths covered that we're going to get covered. We have all the observational techniques available that are going to be available 30 years from now. And so this is the time when we're going to figure out that this is the way this system really is, or we're potentially going to find out this is way too messy and it's not going to ever tell us anything. But one way or the other, we're going to come out of this with a much better understanding of this star system.
In the year 1821, German astronomer Johann Fritzsche was the first to observe that Epsilon Aurigae is a variable star. It was the German Hans Ludendorff who suggested in his paper in 1904 that the star is an eclipsing binary.
27 years later, other observers came along and more carefully followed through its paces and created the first eclipse light curves, and everyone was a bit surprised to realize at about that point, or late in the 19th century, that it was a 27-year cycle to this star, and the eclipses last an entire 18 months. That's a great deal longer than
The way scientists describe nature is through models. A model is an imagined reality created with the use of mathematics. Imagine two stars orbiting their common center of gravity. If they move in such a way that seen from Earth they occasionally block each other out, we call this an eclipsing binary star system. The eclipses cause a regular dimming in the total amount of light. If we draw the total amount of light on a graph, it would look like this for our model. If the light curve of our model matches the light curve from our observations, it is likely that the star system we observe is similar to our model. Astronomers have been able to create matching models for many eclipsing star systems this way. To this day, however, it has been impossible to find a model that closely matches the light curve of Epsilon Aurigae.
And at 5 years old, I can remember going outside and just standing outside and looking at the stars. And I remember my mom coming out with me and just looking at the stars and that. And I think it was just obviously a God-given interest. My 7th grade science teacher taught, at that time, this was back in 1967 range, science was big. And he taught us a big astronomy course. He let me borrow a real nice telescope. I lived next door to the middle school, so I was able to carry it home in its wooden case and everything and set it up. And that just caught me, and I joined an astronomy club at 14 years old, and happened to be one of the fellows in that club was big into variable stars, and he taught me, and it just clicked. I made my first variable star observation of Z Ursa Majoris, which is a binocular star, in March of 1973. And that was it. I was hooked then, and I haven't stopped doing it since.
When I was 4, I think, something like that, I would go over to my grandparents' house every Saturday for Saturday dinner, and they had a bunch of books to help occupy the kids. And one of them was this little book about a family that lived on a space station, I think, in outer space. as they were flying in the spaceship to go back to Earth, it talked about how they were weightless. And I remember a story that the children would pour their milk out into midair and push it into a ball and eat it. And as a child, I thought that that was just the concept of weightlessness and being in outer space fascinated me so much that that sparked an interest. And throughout my childhood, I was very interested in the space program and in astronomy, and had an aptitude for science, and decided to major in physics and astronomy and pursue it as a career.
As far as I can remember, astronomy has fascinated me since I was 4 or 5 years old. I was looking at an encyclopedia and saw some images of the sun that were in 2 different wavelengths. So the sun, how it appeared in X-rays, and the sun, how it appeared to our eyes. And they were different, and that just fascinated me. And throughout my teenage years, I built telescopes in my yard. I was an amateur astronomer. I just fell in love with the subject, and went that sort of either extra step or that different step of saying, okay, I like amateur astronomy, but I want to do this. I want to learn, I want to understand, and took the time to work in math and physics and science and eventually get my PhD, and it just has never stopped being exciting to me. It's different now than an amateur career in some sense, but I love the amateur part of going out and observing on the sidewalks with the public, but I also enjoy going to large telescopes on mountaintops and making very precise observations with complicated instruments and computers that do all this processing for me and coming up with answers that way as well.
It's something I have done for as long as I can remember as a child. My parents would take us out and we'd look up at the stars. We would be in remote places and it would be black and beautiful, and we learned all about the sky. And I can remember when my dad put together a telescope and just those first images of Jupiter and Saturn, and I was hooked, and I just enjoy it. It's wonderful.
I myself am a product of Sputnik, in the sense that as a youngster, the Sputnik space race, Cold War facets were what allowed me to get into science. The opportunities opened up and so on, and here I am now a professor of astrophysics some time later. The opportunities are there. A person needs some initiative to find them. They're not hard to find. Places like Adler Planetarium and others around the country, around the world, do all they can to have the outreach to citizens.
The thing that actually turned me on to astronomy in the first instance was my father took me out with a telescope when I was 8 years old and showed me the rings of Saturn and the moon. And I was hooked after that.
I think science has lost its place a lot. I think that technology is interesting to most people. They think about iPhones, they think about the internet, but they don't really think about where that came from. It just kind of is there in their culture, and they accept it and they love it, but they don't realize that that started with scientists and engineers, and those are the kinds of people that needed to make it. And I don't know if they appreciate, even in sports, that a lot of the reason sports can be what it is in terms of, say, uniforms or football helmets or baseball bats or the televised thing of sports, all that was because some scientist or engineer or some technical person worked on some project and developed that.
The cooler science seems in our society, the more interested and more willing to be a part of it and to really invest oneself in learning students will be. Because we know that in our formative years, we're very concerned about what's cool and what's not. And so I think that it's very important, and it's my goal with this project, to try to get it out there that science is cool.
Because we depend so much on science and engineering for our survival now, it would not be possible to sustain our population and culture, our behavior. Now, perhaps it's not sustainable given the way we use energy. However, science derives from the Latin root of to know, or a means of knowing, and it certainly has a proven track record. Whether you're a hunter or gatherer or scientist, you're basically doing the same common sense scientific method, hypothesis and test. And the challenge to all of us as educators or even amateur scientists is to try to convey that method, or at least the advantages of that method, to to the younger generation so that they can at least try to apply it or realize that that's what they're doing in their life, and hopefully have a more successful, more sustainable life as a consequence.
There used to be a time when people would stand and look through telescopes for a long time when we do public outreach, and they'd sit and visit and ask questions, and they kind of rush through now and take a peek and, oh, that's great, and they're off to something else. And I noticed that in school, the kids are not getting what I remember getting as far as just regular physics, astronomy, math type sciences in school. So no, there could be a lot more in school, and it works so well with all the other subjects that it's just a shame that it doesn't happen more in the schools and actually integrate more with other subjects.
There's a lot going on in the world. There are a lot of different activities. There are a lot of different things people want to do, and there are a lot of different things people need to do. Science has to have a certain share of that, and countries that promote it actively and communicate it and educate it actively are likely to gain in prosperity, to lead a higher quality of life than those that don't.
I have no special talent. I am only passionately curious. Albert Einstein.
There's so much we don't know, and there's so much I don't know. And it's anytime you go out, you have the opportunity to discover something new for yourself. And every time I go out, I do. And that you're not looking at the same things all the time, especially in astronomy. The seasons change, the planets are moving, everything is changing a little bit. And for example, just the moon. I mean, you could look at the moon every night for an entire year and still not discover all of the cool little rills and craters and rays and other things that are on the surface of kind of the closest body to us. I probably observe more for fun than data, only because the data aspect is a new one. Finding out cool things that other people have seen and then trying to find them for myself, that challenge is a big piece of it. Putting it together, the puzzle, you get one little piece of it at a time, and you don't know what the overall picture is going to be when you're done. I observe to learn things. You read, you listen to other podcasts, so it provides you with a lifetime of puzzle pieces to go out and find.
When you're doing something like this, for example, Epsilon Aurigae, when you're standing out there at night and you're looking at it in the sky, and it looks just like a point of light in the sky, you can picture 2, 3 stars with a dust cloud, this opaque dust cloud, and orbiting each other, and it's like you're here on Earth, and your mind can take you light years out into space, and that's the type of thing, and that's what gets people interested.
A digital camera uses a grid of sensors to capture a photograph. Each sensor measures color and brightness to represent one tile in the mosaic. In order to recognize an intricate pattern, we need a large number of measurements. So it is with light curves from variable stars. More observations give a better defined curve. If the eclipsing star system is complex in nature, it will generate a complex light curve. This is why we need many observations to reveal the so far mysterious nature of Epsilon Aurigae. And this is where the amateur astronomers make their contribution. Each observation adds to the clarity of the light curve. This is how many eyes together can perhaps see something that so far has been invisible.
All that is valuable in human society depends on the opportunity for development that is available to the individual. Albert Einstein.
I think it's an American thing. It seems like in the last 20 years or so, there's not as much push of science, at least in elementary and middle schools. And of course, that's important. They need the foundational science then, so they can move up to high school to chemistry and physics and biology or on to college. And we've kind of moved away from that, and it's very much a shame. And I think this is part of the reason why we're getting a lot of scientists coming from other countries, and there's nothing wrong with that, but it would sure be nice to get our own people, because we've got smart people in America. I've got a lot of smart students. I've got many students that have gone on to be doctors and lawyers and this and that, and it sure would be nice if we could catch them. And astronomy, unfortunately, does not seem to be pushed very much in the public schools.
I probably would support more extracurricular activities, you know, have the schools support more after-school astronomy, after-school physics. And I think you get support from the teachers, you get support from the parents. I think it's hard that the administration's trapped by budget. But I think there's enough volunteers out there. I know there's enough volunteers out there.
I remember my 7th grade and 8th grade science labs at the school next door. There was a sliding wall into the classroom, and it was a giant. It was as big as a classroom. It was packed full of every type of lab equipment for every type of science. And nowadays, the emphasis isn't there anymore. I don't like just to sit there and teach out of books and write on the board. I take my kids out. I have telescopes with special solar filters because you're there during the day at school, so we go out and look at the sunspots, and that's totally safe.
In terms of popular culture, you know, the fads will come and go, but there are these underlying assumptions and commonalities where things like a public education in the Jeffersonian sense are important to sustain society as we want it to be.
Joy in observing and understanding is nature's most beautiful gift. Albert Einstein.
Well, in this particular project, as you know, the star is very bright, so you can observe it with the naked eye. You can observe it with binoculars, you can observe it with instruments. And making an observation can be as simple as looking at it, recording its brightness compared to reference stars nearby, and then contributing those to the network of contributions. And that observation becomes one of many. It doesn't mean it's less important than all the rest. It becomes one of many. And it's a very simple process to contribute those.
The way the magnitude system works, a lot of people don't understand this, and it's hard when I teach my students at school, because we're used to larger numbers bigger, but in magnitudes of stars, the larger the number goes, it's dimmer. A 0 magnitude star like Capella, which is right by Epsilon Aurigae, is 0 magnitude. It's very, very bright, whereas Epsilon Aurigae right now is around 3.0, or 3rd magnitude. The 3.8 star is dimmer than that. So as you go upwards, higher numbers, the star is actually dimmer.
So the first thing you have to do is you have to be able to find the actual star, Epsilon Aurigae, in the constellation Auriga. And conveniently, there are some great star charts for that, and it shows you the entire constellation altogether. Another thing that helps too is a planisphere that will help you find the constellation in the big picture. But once you know where the constellation is, then the next thing is to find the particular star. Happens to be that one right there with the crosshairs in it. And then you need to take a look at it and try to estimate how bright the star actually is. I observe from the city, and so sometimes I actually need a little bit of help, and I find that binoculars right now are helping the most. And it's not because I need to make the star any bigger, but it does help with light pollution, and it does help if there's any haze as well.
The star chart that has Epsilon Aurigae on it has what they call comparison stars, which are stars of known magnitude that do not change. And the variable stars marked on the chart, so you would expect over a time period the star to change in brightness. So what you're doing is basically making, we call it a variable star estimate.
The next step is to report it back to the AAVSO, which is the American Association of Variable Star Observers. And you can do that through the Citizen Sky website. There's a special page for that. And you go in and you need to log in the date that you did it and the time that you did it, and then what your estimation of that magnitude was, and then what the comparison stars you used were.
We will collect all of that data. It's accessible back to the citizen astronomers. You can log on to the website and look at the data yourself if you want to try to figure out what's going on. But we will also be passing all of that data on to professional astronomers doing data analysis.
Don't say you can't do it.
Harlow Shapley, who was in the early part of the 1900s, early middle part, he made a statement that I quoted to my students at school, and it's on my PowerPoint. He said, good observations never die, but theories fade away.
It's not only just this project looking at Epsilon Aurigae and judging how bright it is and logging it in, but there's a lot of other opportunities, and all of the scientists for volunteers to step forward and actually help. And there's more of us than there are of the professionals. There's a lot more volunteer eyes out there than professional eyes. And so when they ask for help and when they say, help us by looking at this, it's a wonderful opportunity to be able to become part of the scientific environment. And everyone can do this. And so, take advantage of the opportunity.
A truly open-minded individual will immerse themselves in the various different realms life has to offer. Making observations of variable stars is a wonderful way to include science among them.
Well, absolutely. One of the things science does is it brings in new understanding to a person. And once they start to see the true connectedness of things, it's a much more rich vista than many other worldviews. There is the ability to finally grasp why things are the way they are, how much they're likely to change, how much control you perhaps have over things.
I think a scientific pursuit, when you're actually looking at things and thinking about them and gathering the data and looking at the data and then using that information to make decisions, to form hypotheses about anything that you're looking at, astronomy, biology, whatever it is, it allows you to kind of take in the world both in a manageable, outlook, as well as step back and take a look and just kind of go, wow, this is just a fantastic place. And these mountain ranges that you have behind you, the Tattooshes, and this volcano that I have behind me, there is so much to be learned, about volcanoes and how they work. And it's a lifetime pursuit, and it provides you both with answers, and for every answer you get a whole lot of wonder.
I think I've always seen societal issues from a viewpoint of I understand them, but why can't we just solve them simply because, after all, we're such a small part of the whole universe? How can these problems be all that, hard to solve, or all that, devastating that we have to, go to war, or we have to, push other people out of our cities or something? Where why aren't we all together? Because this is what we have. We're this little spaceship Earth, right? We've heard that term a lot at this meeting. We're this little spaceship, we're all on it. It could be all there is, and we're in this vast universe.
I think we as human beings, somewhere in us, all of us have this quest for more in some way. There have been many human explorers that explored the globe, and I see scientists, and particularly astronomers, as being just that. We're just explorers of a different realm. And so I think that studying science, studying astronomy, fulfills in many people that need for more, to learn, to understand the world around us.
There is no better way to expand our understanding of nature than to participate in its discovery. By contributing their observations, thousands of amateur astronomers all over the world fulfill their desire to be explorers of a different realm.